we finished the fundamental theorem of asset pricing, where we learn that given enough securities with their prices, we can price any other payoff, which is in the linear span of the payoffs of the securities given. That is what we learned. And then we got very enthusiastic, or at least I got very enthusiastic, and said, well, if we can price anything, let's get into some interesting other alternatives. And then we came into the issue of decision-making, pricing, decision-making to affect prices. And I presented a type of options. I call them exotic options. Maybe that's not the right term. Exotic options is a term which is used in the industry to denote unusual options, options that have many bells and whistles, and no one will call an American option exotic, but many people would not have seen swing options before, so that's why I call them exotic. And the whole point of this discussion is, first of all, I presented this in a multi-period setting. Multi-period setting is the only one where these things make sense. You cannot have a swing option or even an American option on a single period. Okay, we're pricing decision-making. We need times to make decisions. If there's no times to make decisions, we cannot do that. We cannot price anything. And I presented as a warm-up the same example we have seen over and over and over again over 2 periods, which is the pricing of a European call. And we priced it going backwards. Okay, if that's the stock tree, then that will be the option tree, which has trivial values at the end. And to find the rest, we just go backward, treating each of those branches as the basis for our decision making, which in this case is only pricing. So each of these branches is a European branch, as we saw earlier. Okay, and that allows us to find the price of the option there, the price of the option there, and then we simply view the option today as another European branch where the price tomorrow is known, the price today is unknown. We solve for that and we get it. That's what we do. And you can do this by running more and more and more intermediate points. You can do this by having almost a continuum of values. The continuum is what I'm doing today. Okay, so today I will go into the continuum, but in the last week there was no continuum. It was just as many as you want. There's one thing that we need to learn. The one thing we have to be very careful as we move this to the continuum, and this is the purpose of the second half of today. So we saw that, and we've seen this many times. Goes back to the 33-cent game that we did in week 3. We're in week 5. Okay, so that was 2 weeks ago. All right. Now, what about if we consider an American option? An American option is one in which you can collect your money without waiting for maturity. You can wait your money before you can get your payoff before maturity. We saw that in this case, that was an interesting point because the stock is $1.50, and if we end up there, we can exercise the option, and the exercising the option will give us 75 cents because the strike price in this example was 75 cents and the value of the stock is $1. So $1.50. Okay. Sorry, there's a question on the chat, which I think I'm going to interrupt this to address the question in the chat. It seems important. Okay, so it says, is next week's lecture? Yes, so this week and next week on Zoom, both. Okay, and then in person after is reading week, so after that will be 27th of February, that will be in person. Okay. Yeah. Okay. Yeah, it was mentioned in class. Yes. All right. I didn't put it on the website as an announcement. I think I sent an announcement on Kirkus. But anyway, we announced it in class, and we know. Oh, yeah, sometimes my video comes with a delay, like now. I don't know why. Okay, I think I have no idea. If it bothers you, you let me know, and then I do something. Like now, it's a very big delay. I don't know. I think it's just my video. Yeah. Okay. So I go back. If the video quality bothers you because of a delay or something, let me know, and then I will stop and revisit. I know when it's on a delay, I can monitor that. Another question. When will last lecture be posted? Because the video was removed from YouTube. Really? I posted that yesterday. I'll check during the break, okay? The video should be there. Maybe if someone can check the video should be there. There should be the 4 videos there. Someone please check and let me know. If not, I'll check during the break. You can check more easily than me, perhaps. Okay, so back to the topic of the lecture. So the case of the American option is where we can exercise early. In this case, I'm looking at a strike of 75 cents. And as I said, that is an interesting point because the stock is $1.50. So the payoff of the option would be 75 cents. If you exercise at that point, you get 75 cents. And if you don't exercise, then what you have is you have a European branch, you price that, and then you calculate the price. It happens to be 75 cents also. So this is interesting, and we call this point a point of indifference. We're indifferent whether we exercise or not. You can exercise and collect your payout, or you can wait. And the value of that is exactly the same. All right, so that is what we saw last week. I think that was interesting. I think Theo has a question. Go ahead.
Yeah, I was just gonna ask about like the point of indifference. So like I understand that why we're indifferent, because if you exercise now or if you wait to exercise, like on average you get the same payoff. But I was just wondering, because if you exercise now, you have a guaranteed payoff. But if you wait to exercise, it could potentially be lower.
Yes.
So aren't you taking on additional risk by not exercising, and you're not being compensated for any additional risk?
Okay, a very good question. Very good question. Your question actually has many questions built into it. Okay, let me start with your last question. I said, are we not taking any risk? Okay, we haven't defined what risk is yet. What you're saying is that I have uncertainty. I don't know what my payoff is going to be. It could be higher, could be lower. Okay, and so you can say, well, if I am, if I don't like indifference, sorry, if I don't like uncertainty, then I cash it in now. So from that perspective, you would do that. But you see, that introduces the notion of risk aversion. The reason our risk neutral measure is called risk neutral is because you're neutral to risk. In other words, we don't care about indifference. We have a way of pricing that we know we could replicate the portfolio, and therefore the price is 75 cents. Do you understand what I'm saying? I'll say it again. I'll start with, I gave you the answer backwards, and now I'll give you the answer forward, and see if between the two it's all clear. I can say that the price of this is 75 cents despite the fact that I don't know how much I'm going to get. Why? Because I can build a replicating portfolio. You agree with me that a replicating portfolio will cost 75 cents and has no uncertainty, right?
Yeah.
Exactly. So suddenly the uncertainty that we see there is not real uncertainty, because if you don't like the uncertainty, you build a replicating portfolio, it has exactly the same payoff, uncertainty is gone, and the value is 75 cents. And that's where we can say that the price of this option is 75 cents. Okay? Are you with me? You see the 75 cents? Yes?
Yeah.
Good. But now the interesting thing is your second part of the question is very interesting, because you're saying, if I don't exercise, I have uncertainty, I have risk, right? And then I'm saying, yes, so if you don't like risk, if you don't like uncertainty, then you exercise. But if you don't care, and that's what risk neutral means, then the price is 75 cents. And in our case, because we have replicating portfolios, we are risk neutral. Why? Because it's not a matter of certainty or uncertainty. If I don't like uncertainty, I have the replicating portfolio, and that will be certain. And that's why the name risk neutral, that's where the name risk neutral comes from. Do you see? Think of the replicating portfolio, and that, see, from the replicating portfolio perspective, if you only look at the replicating portfolio, you would not be asking the question.
Right.
With 75 cents, I end up with a portfolio that could do this or could do that. I don't care. At the end of the day, I don't make any money. I don't lose any money.
Okay, yeah, that makes sense.
Right? Exactly. Yeah. But if you only think about the replicating portfolio, then you would not have asked your second question, which is the interesting one. From a risk neutral perspective, risk uncertainty doesn't exist. Everything is predictable. Do you see?
Yeah, no, I understand now. That makes sense. I just wasn't thinking about the replicating portfolio.
Look, there's a course like this for a reason. These things are not obvious. That's why people get the Nobel Prize for coming up with this type of thinking. Okay? But once you understand this type of thinking, then everything is different. Everything has a different price. And that's why the nuclear physicists or the particle physicists in the 80s were making a killing, because they understood something that the rest of the market didn't. So they had access to arbitrage opportunities. They had access to information asymmetry. And the name risk neutral is because, in fact, after all of this is said and done, what seems risky, what seems uncertain is not. And I remind you of another thing that we saw. Do you remember I told you about the case of Bankers Trust and Procter & Gamble, that swap? When a person, individual, tried to sue, or actually sued Bankers Trust for gambling, which is illegal in the state of New York. This is not gambling. Under the risk neutral perspective, I'm not going to say measure, from a risk neutral perspective, we're not gambling. All of these uncertain events, they are really the outcomes of a portfolio that we can build that has a guarantee, that has a real price, and you can buy, right? Okay, so I think it's clear. I gave you a bit of an overkill of an answer because your question was very good, and because I suspect many people were having the same doubts as you. Okay?
Okay, thanks.
Good. No, thank you. Good question. Very good question. All right. So, and that's the point. Well, when the exercise, early exercise is the same as the late exercise value, then we call it indifference, because you can exercise or not. Doesn't matter. The price is the same. The value is the same. Okay. So that was good until I introduced the concept of a swing option, which is an American option where you have not one but several exercise options, or several options to exercise, which all in itself would not be interesting. If you have several options to exercise, it's like you have several options. You have 10, you take the price of 1, multiply by 10. But if I introduce the restriction that you can only exercise each of them once a day or once each node, then we have to think. Then we have something interesting that needs to be considered. Okay, so let me, hold on. There's a question in the chat from Chris. How realistic is it for a real replicating portfolio to achieve close to risk neutrality? Well, 100%. In our context, 100%. If there are no transaction fees and markets are complete, 100%. Actually, he says, I assume risk can be neutral only if you have a good enough model of S. No, risk neutrality I will have as long as every payoff can be replicated with securities whose prices I know, and there are no arbitrage opportunities. That was the theorem that we saw last week. If every payoff can be replicated, then we're fine. Let me give you an example. I remind you of an example where these things are not like this. We have a stock that is worth $1 today and can be worth $2.50 or $1 tomorrow. 3 outcomes. There we have uncertainty. There we don't have a risk neutral measure. There we don't have the ability to construct a replicating portfolio. We have more events than securities. Remember? There we don't have what we have. However, if I say, well, but the price of the option that gives you $1 if it goes up is 33 cents. Then we're good. Then we have a complete market. And then now, again, everything can be priced and uncertainty is removed. Yeah? And that's the theorem that we saw last week. That's why I wanted to do the theorem. And that's why I wanted to actually even give you the proof. Because from that theorem perspective, all of these things now have meaning. Okay? All right. Yeah, all good questions. All right, so let me go into the swing options. Again, reminder, I show you the Air Canada Flight Pass. It's an example of a swing option. We discussed that. And the key to pricing an option, a swing option with, say, 10 exercise rights or 9 or some number is to start with 1, then go to 2, then go to 3 until you get to the number of exercise opportunities you have. And the things that when you only have 1 exercise opportunity, that is the American option. That is what we already saw. That's the key to pricing this. That's the key to pricing this. The way I did not mention that the pricing of the swing options, the original one, was done by a former postdoc of mine, Stathis Tompaidis, in Texas, University of Texas, with his colleagues there. Okay, and that was done in the year 1997, 98, something like that. It is one of the. I'm very proud of this result because he did it. He was in Toronto for a year, and so these things that I'm telling you are things which, I mean, I wouldn't say they are, they were done yesterday, but they were done almost in this century, almost. Okay, so the key is you have to price a 2-up swing option. 2-up swing means a call option with 2 exercise opportunities. Then you start with 1. And 1 is an American option. You only have 1. That's an American option. Once you have that, then we go to 2. And the going to 2, from 1 to 2, is what I want to tell you. This is where we do all the thinking today. Okay? So the case of 1 should be easy. It's an American option. I don't have to do it again. It's exactly the same as before. Okay? The key is what happens when I do 2. When I go here. Oh, sorry, this is the 1, this is the 2. And this is the one that I want to explain to you again. This is the thing that very likely requires some explanation, okay? Are you good? All right. So this is the thinking. This is the thinking. I start here. I start there. At expiration, we know what the prices are. You may say, how come I have 2 exercise tickets left at expiration when the stock is worth $2 and my strike is 75? How come I have 2? That could never happen. I say, I don't care. That is not how we do this. It's all conditional, even if the condition has probability 0. We're not concerned with that. If we are at the last day and we have 2 tickets left to exercise, we can only exercise 1, and the value would be $1.25. That's how we get that number. That number is, we have 2, we can only exercise 1, we get 25 cents. And that one is clear. You don't need to exercise anything because nothing will give you any money. So as usual, pricing or valuing this option at expiration is easy. What may not be easy is to calculate the probability that I end up, say, here, or is that even possible? But no, we're not concerned with that. We're not concerned with that. Okay. So let's go one step beyond, and we go again one branch at a time. So we go to this branch. I say, what happens here? Okay. When I'm there, what I have is, if I exercise my option, my stock is 75 cents. If I exercise my option, I get nothing. Sorry, that's right. If I exercise my option, I get nothing. If I don't exercise, then I value the European branch, and I see where with these numbers, the value of that will be 12.5 cents. Therefore, the value is 12.5 cents. Is the higher of the 2 values. It's 12.5 cents, and I do not exercise. It's clear why I don't exercise. I collect nothing. It's clear. And say, well, if I don't exercise, at least I may make some money tomorrow. True. However, again, we don't think like that. We don't think from an uncertainty point of view. We think from a certainty point of view, which is the price of this is for sure 12.5 cents. And if you have any doubts about that, find the replicating portfolio and then you'll be convinced. So it's 12.5 cents. That's if I don't exercise. If I exercise, it's 0. Which one is better for me? 12.5 cents. That's the price, and I don't exercise. Done. Okay. Now we go to the one on top. Here, what I have is, I have my stock at, what's the price of the stock? I forgot now. It's $1.50. So stock is $1.50. And if I exercise 1 book of tickets, I get 75 cents cash, and I get another option. Another option is like a flight pass with only 1 flight left, and that has value. What's the value of that? What's the worth of that? The worth of that is the value of the European branch that we calculate happens to be 75 cents. So if I exercise, I get a total of $1.50. Some in cash, some in a security. $1.50. If I don't exercise, then I have an option. I have a European branch. I calculate that and I get that the value is 75 cents. So $1.50 versus 75 cents. Which one is better for me? $1.50. So here, the price is $1.50 and I exercise. Obviously, it's not a point of indifference anymore, clear. But I exercise. And that's it. And now I go to today and I play the same game. What happens if I exercise? The stock is $1. My option will give me 25 cents plus the value of the European branch. That European branch happens to be 1/3 if you do the calculation. So the answer is is 58.3. But if I don't, okay, that is if but if I don't exercise, I calculate the value. Sorry, I don't know what I said. I'm going to repeat because I'm not sure that I said the right thing. Okay, I may need to repeat. Now, in the meantime, there's a question here. Why not simply price linearly? Let's see, B the cap, T the total return. I don't understand your question. I don't understand your question. T.
So basically, you have C European option at that point, right? Because that's American option actually, and then you can just treat them as C American option, and then the remaining one you just treat them as European. So that's why we buy linearly.
So sorry, you're calling C the American?
The cap, the number of options that you.
Oh, the number of options.
That you can sell, like that you can exercise at a not at a. Yeah.
But you cannot. No, wait. Okay. So look, I don't know. Maybe you're right. Okay, but there's one thing here that looks strange to me because we can only exercise once. So the fact that you're multiplying.
I was thinking like, let's say you have like the cap is not 2, but.
Yeah. No, I'm not doing that. No. Then in that case, I think your formula is right. But no, my restriction is I can only do one per node.
Right. Yeah.
Only one per node.
You can do C per node.
Yeah. So yours is the original. Yes. In fact, I think on the course website, I think you have the original paper, or at least one paper. I forgot if maybe it's not the original. You have one paper on pricing swing options. Then yes, this is how you do it in reality, in practice, right? And then you will see something similar to what you wrote. Yes, but here I'm addressing the simple case in which I can only exercise one per time or per day, so to speak. If each node represents a day, I can only exercise one per day. Okay?
Yeah, in that case, you can just, it's like you have an American option and a European option. That's
right, and exactly. And you have a European option. Actually, let me correct what you say. You have a swing option. Happens to be American in this case, but if you're doing, say, a book of 4 tickets, and then you're comparing 3 with a European, right? So it's actually a swing option with 1 exercise ticket less, right? It's just that in our case, because we go to 2 to 1, 1 is the American, 2 is option. But if we do, say, from 3 to 2, you're jumping 3 is not what we're doing, right? Of course, the last 3 is an American 3, but the other 3s are all option. They're all swing 3s, right? It's very nice if you think about it as jumping 3s from one tree to the other. That's what that would be, I guess, the monkey algorithm. I guess you go from one tree to the other, and every time you jump a tree, you collect the payoff, and you collect the payoff and the value of where in the other tree you land. And that's the comparison we make all the time, right? We jump trees or we stay. If we stay, it's a European option. We know the price. If we jump trees, we know the price of the other tree that was done earlier and the payoff, and we add them together, right? So if I use that language, jumping trees, I like to use that language. I think it's very visual. So in this case, at the node today, I have the option of staying. If I stay, what I get is the value of that European branch. Or I have the option to jump. If I jump to which tree? I jump to this tree. I jump to this tree, right? Which gives me an option worth 33 cents and a payoff which is 25 cents. Again, jumping gives you the payoff and the value of the tree below, so to speak. And in this case, it's 33 cents. Turns out that in this case, it doesn't matter what I do. I get 58 and a third dollars. So 58 and a third cents, no matter what I do, whether I jump or not. So it's a point of indifference. So here we exercise, and this point is a point of indifference. Doesn't matter. Okay? And we're done. And I've done 2, but I could do 7. The only thing is when I do 7, I have to start with the American. Then I go to the one with 2 that we did here. Then I go to the one with 3, knowing that every time I jump a 3, I go from 3 to 2. But 2 was already done, right? And 4 to 3, 5 to 4, so on and so forth. Is that clear? Okay. There's one footnote, and I hope this footnote does not confuse anybody. It's just that I need to tell you the truth, 100% of the truth. Okay. When we fill these trees, we need to we need to, of course, know the price, but we also need to remember what the price would be if we don't exercise the European brand's value, so to speak. We need to keep a memory of 2 values at each node. Why? Because when we jump trees, the value you collect is the value if you don't exercise, because you cannot exercise again. Otherwise, it could happen that you jump from one tree to the other, to the other, to the other. You jump 3 trees all in sequence, and you collect 3 payoffs, and that's not allowed. Okay, so we have to make a very small modification to what we said, and that requires that at every node you keep 2 values. If this confused you, then I would say ignore it. Just remember that it's something that maybe is not quite right. Okay? And then we're done. So it wasn't 5 minutes, it was 35 minutes. But is this clear? It's a very good example of how option pricing can help you price lots of different situations. And in this case, actually it helps you make decisions, and it actually tells you the price of making decisions, or the value of making decisions. Question? In the bottom right, why is the value 0 not? Oh, because this is an option. An option does not force you to buy. It's not a futures contract, right? In an option, you see, you have the right to value the stock, which is worth 50 cents. You have the right to buy it at 75 cents. What do? Don't buy it. In other words, what's the payoff? 0, not negative. Options never have negative values. Yes, I know. Yeah, Chris, good. Any more questions? I think I asked all the questions in the chat, but I'm about to leave this topic entirely. I want to start with the continuous time finance. So for that, I want to make sure that everybody understands this very well. I don't mind waiting to make sure there are questions, because now we are really going to, not to a different mountain. We're actually taking a plane, we're going to a different country. And then we're going to start claiming mountains in a different country. Okay? This is the end of the discrete pricing, discrete time pricing part of the course. Okay, so I hope it's understood. I'm going to take an early break now, just because I need to change I have to change my display. I have to change, but also the type of thinking we're doing now is completely different from this. Completely different. Today we're going to do actually a lot of math, but we're going to do it the fast way, intuitive. But it's going to be now. I'm going to start with mathematical considerations, and then we will get to finance considerations. So we take a 15-minute break. We come back at noon. And then I will continue for the next 2 hours with everything we need, continuous time finance, stochastic calculus, stochastic analysis, all of that, all in 2 hours. Okay, so I see you at noon. We're about to reach infinity and beyond. So this is what I'm doing now. We are going to abandon the realm of finite, discrete time finance to get into continuous time finance. And I'm going to do that by explaining what a random walk is, what it does for us, and the most important thing is to explain one characteristic which is extremely important. So here's the question. This is the same graph we have seen before in class. And the question is, how do we extend the discrete time model? Let me tell you a very interesting mistake that every rookie makes when they go from discrete time to continuous time. And it's the best way to understand a very important characteristic, which is what actually makes this mistake very, it's a bug that is very hard to fix. I would be betting that if I ask all of you to take this model that we have here, it's a model that has two. I say, well, it has, I want to call this dt, these are the increments. I want to call these ds, these are the increments. And I say, do a program in Python or some programming language where the price and the time increments are variables in your programming. They are external parameters. Okay, so you can make them as small as you want. Okay, so you have a full, say a full year to cover, and let's say that I give you n days. All right, so I give you a parameter. So pick n days, make the time increment small and the price increment small, so that as an external parameter you can make n to be 360 or even more than 360 if you're going to allow trading throughout the day, and implement an algorithm that does this. We understand this. We know that it's no difference if we have 2 or 2000 time steps. You can program this in Python by going backwards. Very easy. Understand? Yeah. What would most of you do? What would be the? I'll tell you what most people do. Okay, maybe you already have seen this before. Maybe you're smarter. What most people do, they say, okay, so if it's a year, dt. I want to write this by hand, not because I want to make a mistake. Okay, I want to make a mistake. That's why this is not written in LaTeX. I want to make a mistake and write it. I'm going to say dt is, let's say, 1 over n. I'm going to use n to be years and in these days. So my dt is going to be 1 over n. All right. And then you're going to say my ds is about also 1 over n. And that way, as n grows, I have more times and smaller price jumps. Okay, I'm writing this by hand because I'm making a mistake. What happens if I do that? And then I write my program in Python with this increment. So this is in dollars, and this is in time. And I write this in Python, and then I let n grow, 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 grow. So I have more and more and more and more nodes, smaller price increments and smaller time increments as n grows. What will happen? What will happen is that as you run your Python code with increasing values of n, the value of this option is going to be 0. It's going to converge to 0. And it almost doesn't matter what numbers you pick for the stock price or the payoff. It's going to converge to 0. Why? Who can tell me why? There's a very interesting reason, and that is what we're going to find out. To answer why it converges to 0, I have to stop thinking like this and think in a different way. When you do what we are doing, which is you make finer and finer and finer stock trees, and therefore option trees, there's a certain proportion that needs to be kept, and it's not what I wrote here. If you have the proportions that I wrote here in the limit, you're going to get a trivial answer. That's what will happen. You can do it. You can write the Python code. It won't take you very long. Then continue to take n, increasing and increasing values of n, and you see the option price will converge to 0. So I hope I have your attention. For this option price to work, I need to do something different. And now I need to forget about finance for a minute and do math, only math. This is math that maybe you have already done. I have to do stochastic analysis. Actually, it's so simple that I'll call it stochastic calculus. I'm going to do stochastic calculus for you. The stochastic analysis is the formalized version of a stochastic calculus, and it's more complicated. So we'll do stochastic calculus, okay? Or without proofs, with intuition-driven expressions. So let's start with a very simple experiment, and I think you will understand this. I have here what's called a random walk. What I do is at every step moving to the right, I flip a coin. If the answer is +1, I go up. If it's -1, I go down. And I do this many times. Many times. I could now, sometimes I do this, I didn't want to do it today. Sometimes I have a polling software running and I ask everybody to do a poll. I ask you to flip a coin and give me a plus or a minus. If it's about, we are 32 people here, so it's about 30 because I am 2. With 30 people, what I will see is that when you flip a coin, I'm going to get some heads and some tails, and the balance of that will push me up or down. Okay, so I can simulate with all of you flipping a coin, I can simulate 30 of these steps in a random walk. I can easily do that. You understand what I'm saying, right? You flip a coin, you get. So let me ask you a question. Where do you end up? Where do you end up? What do you think will be the expected value of my experiment when I have all of you, 30 of you, flip a coin up and down? Now, we're not going to do it. But I want to know what your intuition is. 0. You think we'll end up at 0? Actually, we are not going to end up at 0. We are not going to end up at 0. We're going to end up, I'm going to make a guess, at about +5 or -5. Okay. What happens if I, instead of being a class of 30, I take every student at U of T today, every student, we have 100,000 students. I have 100,000 students and I ask everybody to flip a coin. Where will I end up? +-1? You think so? Really think so? I flip 100,000 coins and I'm going to end up at +1 or -1? Really think so? ±100. That's an interesting answer. Who can tell me where we would end up? You understand what I'm asking, right? Imagine every student at U of T flips a coin and I do the accounting. It's extremely unlikely I will be at 100. Where do I expect to be? It's about 300. It's going to be about 300. Okay, it's not important anymore. It's not important anymore. What I want you to, what am I doing here? What am I doing here?
Square root of 10 times 100.
Sorry?
Square root of 10 times 100.
Exactly, the square root of 10 times 100, which is about 300, right? 314, more or less. What am I doing here? So this is what I'm doing here. Let's mathematize this. Enough with following your intuition. You know that intuition and mathematics, they stopped being not good friends, but there was a bit of a divorce between mathematics and intuition in the latter part of the 19th century. It's when conjectures started to show up. It's when mathematicians were doing mathematics in high dimensions where things are very counterintuitive, and then humans lost the ability to imagine math and do math only with their imagination. Up until then, it was no problem. People did math with their imagination. But at that time, there were some phenomena that started to happen that mathematicians couldn't explain, and there were actually arguments in math conferences. People were fighting for what was true in dimensions 4 and 5, right? And then very quickly it became, well, not very quickly, or it took decades, but it became clear that mathematics was getting sophisticated and you needed a formalism. This took 50 years to develop. You probably know Whitehead and Russell and Frege and a lot of these people that are responsible for the foundation of mathematics and the axiomatic math which we now do. The fact that we prove things to you, especially in the more abstract calculus courses, is because for a lot of the math we do these days, intuition, it doesn't get that far. Okay, so we need to have a way of, and this is one example. This is one example where if I continue down the intuitive path, we'll get to a not interesting. It's not a bad place. It's a trivial place. Everything has price either 0 or infinity. There's nothing to do. Okay, and finance for sure would not exist. So we need to be very careful now. Very careful. Whenever you reach infinity, you have to be careful. Okay, either infinity because it's very large or infinity because it's 1 over infinity very small. You have to be very careful. So this thing that I'm doing is not going to work. I could continue like this and I could explain things and you will not understand even if I told you the right thing. By the way, I could easily lie to you, also appealing to your intuition about infinity. Okay, you probably know this. I don't know. I don't know why it just occurred to me. If you probably know this example, it's not that it's related to this. It's related to the fact that intuition at some point just is not something that we can do. You know this, right? If I take a sorry, to this. I don't know why I decided to do something interesting. Just if I take a circle, semicircle, radius 1, you know what that length is, right? What is that length of the semicircle of radius 1? It's pi, right? Yep. And this is 1 over. If I take two semicircles like that, what's the length of the two semicircles? Anybody? In the chat. It's also pi. Yeah, it's pi. If I take 4 semicircles, what's the length of that? It's pi too. So if I take infinitely many semicircles, the length of that is pi. That means that pi is equal to 2. Yeah? You thought pi was 3.14 something? No, pi is 2. Pi is 2. Some of you are smiling. Is it because you already knew? Obviously, pi is not 2. Pi is 3 point something. What happened here? What happened here? Again, we breached the levels of mathematical intuition. Yeah, that's right. Right, Daniel, you cannot bring the limit into, what we're doing here is something very interesting. We're bringing the limit inside the integral and a derivative. The length is the integral of the square root of a derivative square, right? We're bringing the limit all the way inside. We know we cannot do that, but we know we're going to do that now. In the year 1850, there was no limit. The limit did not exist as we know it now. So people were doing all sorts of things like this, and they seem intuitive. That's what we're doing now. We price a stock tree, and if we price an option tree, and we create Python code to admit any number of nodes where there's the time and the price, they just become both small simultaneously without a proportion, we'll be making a mistake like this, and then pi will be equal to 2, or other terrible things. Okay, so we need to mathematize things. We need to be a little bit more careful. All right, so let's be more careful. Okay, that's how I like to be more careful. Now we'll understand something. When we flip coins, what we're doing is this. I have random variables, independent, identically distributed, and I'm adding them up, where n is 30 if I do it with you, or 100,000 if I do it with all of u of t. Okay, or 6 billion if I do it with the whole world. Yeah? Okay, great. What do we know about this sum? What do we know about this sum? Well, let me go really slow. If at each point I move, say, dx units to the right and dy units up and down, okay, or if this is my time increment and that's my stock price increment, then what I know is that after I do all of these experiments, that's where I end up in time, and that's where I end up in price. In other words, the price is that sum. Right? It's my random walk. That's a random walk. You're all with me, right? It's all clear. It's nice formalism. Maybe you like the picture more than you like all these formulas, but the picture took us to the wrong place. The formulas, this formalism will take us to the right place. And this is the right place. You probably know the central limit theorem. I think I asked you. I think you knew what it is. What is the central limit theorem in case you have never seen it? Which I doubt. Actually, you shouldn't be in this course if you've never seen this. What the central limit theorem says is that that sum that we find there, that sum, this result of flipping 100,000 coins or more, that sum has this property. If you divide the sum by the square root of throws, not the number of throws, the square root of throws, right? That is distributed like a Gaussian distribution. Which means that if I have every student at U of t flip a coin, according to this, the sum is going to be of size more or less equal to the square root of the number of students at U of t, the square root of 100,000, which is about, let's say, 300. Okay? We have about 300 square root students at U of t. And that's why if I do this work, I expect to be at a distance of about 300. And that's because you probably know that if I do this with the Gaussian distribution, that's what I'm asking, the answer is about 300. When I have my sigma, in this case, this is 300, right? Where is this into 1/2? That's about 300. That's what I meant earlier, and that's how I know the number of the result, or how far in my random walk I would end up. There's something very interesting here. I mean, I don't know, I assume you're very good at this, but this has some very interesting applications, this way of thinking, right? By the way, you probably know, you probably know. What happens when you do a random walk in 3 dimensions, not in 2 dimensions? Well, when you do a random walk in 2 dimensions, you get this, you get that. But when you do a random walk in 3 dimensions, you actually you have nowhere to go. Okay, your expectation is the origin. That's why if we live in a 2-dimensional world, right? The Earth is 2-dimensional. Not that it's flat. That didn't mean that. It's 2-dimensional. Right? So that's why viruses can actually propagate, and they follow this probability distribution also. In 3 dimensions, there will be no viruses. There's only viruses in 2 dimensions. So I guess if we were birds, we would have no viruses, I guess. Anyway, I'm going a little bit off topic. But this has tremendous implications on lots of things. Okay, this thing that I'm talking about now, which was done around the year 1900s, okay, shortly after, has tremendous implications, not just for finance, but for many things, epidemiology and everything. So that's why I assume you're all very well versed in this. If you're not well versed in this, I encourage you to be. Okay? I am sure there's been a course where this was mentioned. Please go back to that course and remember what you learned, because that's very, very important, very, very interesting. Now, for us, this has an implication, which is that if we want our limit, the limit of the Python code, do you know what I mean by the limit of the Python code? Okay, where you're introducing n as an external variable in your code and you make n to be as large as you want. If you want your Python code to converge as you take more and more and more of those intermediate times or smaller and smaller time increments, there's a certain proportion you need to respect, which is that your time can be compressed by 1 over n, but your prices have to be compressed by 1 over the square root of n. If when you write your Python code, you do not respect these proportions, your code will always converge to 0 or infinity. So it's a useless piece of code. It doesn't matter how good a coder you are, you're a bad programmer. I think I showed you the video of Leslie Lampert explaining the difference between coding and programming, right? Anybody can code a tree with an increasing number of nodes. But most people coding that will have the wrong programming, because their code would yield the trivial answer all the time. Either it doesn't converge or converges to 0. It does not converge to any other number. It can't. You need to think like the central limit theorem to realize that you have to code, program, taking into account the right proportions. And then, yes, then you end up in a non-trivial place. This is the non-trivial place, the place of the Poisson distribution, which is that one. Now I'm making a connection with everything you learned in probability and statistics, I'm sure. So in a certain sense, you already knew this, but perhaps, I don't know, perhaps some of you were not aware of this from the perspective of this and that. So I can come back to this now. And if I want to do a random walk that resembles what stocks do, then of course I want to take dx to be as small as possible, say 1 over n. But then dy has to be 1 over the square root of n. Note that 1 over the square root of n is much, much bigger than 1 over n. 1 over n is very tiny. Okay? If you don't do that, your program will converge to 0. Or infinity. Okay, let me see. Are we all together in this? Like I said, I like to claim mountains as a group. I don't want to lose anybody. We'll just claim the mountain. That one. Which means that these dx and dy, they need to have these proportions that we have here. Is this clear? Do fish not propagate viruses? That's a good question. I don't know. They do live in a three-dimensional world. I'll have to go and revisit this. Not according to this, okay? Not according to this. The third-dimensional space is too big, it's too empty. So most walks end up, the probability that you meet a virus is 0. Of course, the probability that you meet a fish is not 0. They like to be together, right? So maybe that's why. Fish do move together. Yeah, maybe that's why, I don't know, sharks have less viruses than other fish. I don't know. I know nothing about fisheries, okay? I'm just talking about I'm talking about this from a probabilistic point of view, but I'm glad that you see the implications of the central limit theorem. Chris says it's fascinating. I hope you're not being sarcastic. It is fascinating, actually. It's tremendously fascinating. So many processes that are probabilistic based, and the dimension makes a huge difference where you are. Yeah. It was important during COVID, as you probably know. You know, the epidemiologists that have models for viruses and this and that, that's very highly dependent on many things. There's a lot of very smart engineering also relating to this, because, for example, in restaurants, you can change the airflow to minimize the spread of viruses. It's all engineering. You can do the engineering to design spaces where these things are less mixing. Mixing is the word. Okay. Anyway, I'm going off topic. Is this clear? Before I move on to finance. Well, let me see. Someone to the chat. No, so nothing in the chat. All right, so I assume it's clear. That means that we know how to do Python code for increasing nodes. We can price now our American or European options with a number of nodes, so that we get a convergence of the code as the number of points, intermediate points, grows, right? And what I want to do is I want to make a connection between this and something else. I want to do physics now, and there is a reason why I want to do physics. I want to do something that Einstein discovered. It was around the same time, 1905. I think he wrote this paper. And I want to derive the heat equation the Einstein's way. And the reason is because what Einstein did in 1905 is going to be very similar. It's actually very similar to what Black and Scholes did in 1973 for option pricing. So allow me, I'm not going to talk about birds, fish, or viruses now. I am going to talk about heat, which was perhaps the easiest, the most common diffusion equation. I'm going to talk about diffusion processes, and I'm going to do that the Einstein way, because we already learned this. I want to see one immediate implication of this, and that's the heat equation. Okay? So allow me to spend 10 minutes doing some physics for you. It's important, because we'll do the same thing when we do finance. And what I have is this. Einstein had he said, if I want to understand how heat diffuses, he didn't use that word. What I'm going to do is I'm going to do a model in which the following is happening. This is a one-dimensional rod. One-dimensional. You can do this in 2 dimensions, 3 dimensions. It's up to you. The argument is the same, but it's easier to make pictures in 1 dimension. So that's a one-dimensional rod. And it has a certain heat distribution. It's given to you and has a certain heat. Maybe it's very hot here and it's very cold there. Whatever. It doesn't matter. It has an initial heat distribution. And the assumption we're going to make to get our physics is that the heat of a certain particle in the future, 1 instant after now, is going to be half of the temperature of its neighbors. In other words, each particle, think of a rod as a series of, each particle lends its energy to the neighbor. And that's how the temperature moves to the right and to the left. Okay? We're going to follow this principle. It's written here. That's my principle. The temperature later, an instant later, is the temperature now, a little to the right and a little to the left, averaged. In other words, I have this diagram here. The temperature now is 1/2 of that plus 1/2 of that. Looks plausible, right? You can say, oh, well, I mean, why is it 1/2? Was it not 2/3, 1/3? I mean, this is because this is, I'm assuming this material is what's called isotropic. Isotropic materials is where the temperature doesn't care if we're going to the right or to the left, so it's 50-50. Okay? And maybe that number is not 1/2, maybe it's another number. As we see this, let's assume this choice of units so that things are simple. The thing is that if the minute I make this assumption, okay, what I can do is I can calculate the temperature at any point in time as follows. The change of temperature at any point in my rod, that's the point, x, x, x. Okay, and the difference between now and later, that difference, in other words, what you would call the partial differential of u with respect to time times the time increment, that difference, which is that, will be, because of that expression, equal to this. See, this expression is the same as that, where uxt is added here with the number 2. Therefore, that is the second derivative. That's the second derivative, the second discrete derivative of a function with respect to x. So it's there. That is the same as that. And this is the second partial derivative of u with respect to x. There you go. Einstein's paper in 2 minutes. Why? And this is the key. So far we haven't done anything. But this is the key, because if dx squared is like dt, which is what we said earlier is the case, if these two things are the same, then that's my heat equation. Anybody has never seen the heat equation? Read it in the chat. Everybody should have seen the heat equation. Okay, if you have not seen the heat equation and you don't want to write down, I don't care if you write down your name or you write down anything. If you have never seen the heat equation, please find it and learn something about it, okay? Something more than what I just told you. It's a very interesting equation. It's the simplest example of a diffusion equation, and we know a lot of things about it. And in fact, it's going to be critical for our understanding of option prices in continuous time. It's going to be crucial for our understanding of continuous time finance. So because of our discussion earlier, of course, this number 1/2 is related to the specific heat capacity, I think like that. Because what we learned earlier, that dx and that dx, where they kill each other, they're the same, and the resulting equation is the heat equation. Why? Because of this. Because of the random nature of my heat transfer mechanism here. So that's what stochastic movements do. They kill themselves. They kill each other. They have a lot of cancellations. Because of that, each movement has to be bigger than expected. Otherwise, the cancellation will make them trivial. Nothing will change. The heat will stay the same. It's not going to go anywhere. Okay? Another example of what we said for option pricing trees. Okay, so this is Einstein's theory. And if a diffusion in a one-dimensional rod leads to the heat equation, a diffusion in an option tree is going to lead to a similar equation, which is the Black-Scholes equation, which I will do next week. I don't think I want to do that this week, although I think I would have time. As usual, I prefer not to make you drink from a fire hose. I am doing something, I think, very substantial. Okay, and I think I want to do the Black-Scholes equation next week. I think, unless you tell me otherwise. Okay, is this clear? Is everybody with the group? Are we all together? It's important for me that we're all together here. Okay, so we're all together. Let me continue. And now this is the type of formalism, or I would say informalism, that we're going to be adopting. I say informalism because I'm not giving you definitions, I'm just giving you expressions which will work for us. That's why I call this stochastic calculus and not stochastic analysis. There's a difference. So I'm going to define Brownian motion intuitively as the movement of a object, particle, price, whatever you like, and it moves up and down at every step with a probability of 50%, but it moves an amount which is the square root of the time increment. Okay, so the time increment could be a second, a millisecond, then the movement is going to be the square root of that. That's what's important about Brownian motion, that the vertical movement is the square root of the horizontal movement. Horizontal being time. You see, this is the same thing that I've been saying earlier. Are you all with me? Yeah, the same thing. Well, if we follow this convention, then by the central limit theorem, as we saw earlier, after x seconds, I'm going to be located in a certain point in space x, governed by that probability distribution. It's the Gaussian with variance t. Standard deviation is square root of t. The picture is here. Okay, so I'm back at the experiment of flipping coins with the U of T students, all 100,000 of them. Even better, flipping coins with every person in the world, all 6 billion of them. That's the distribution I end up having. It's a Gaussian distribution according to the central limit theorem. But it's very important, that in this case, if I use the coin flipping experiment, and yes, each step I move could be 1 over 6 billion if I'm taking everybody on Earth. But it's very important that the price of each up or down coin flip, the price is the square root of 1 over 6 billion. Otherwise, the model is trivial. It does not converge. I think this is well understood by now, yeah? Okay. All right, so then with that, equipped with that, I will define for you, and define, of course, in our informal setting, I will define for you Ito processes defined as follows. And they're usually defined like that. Mathematically, they are defined like that. They're defined through stochastic integrals, not through stochastic differentials. But I'm not going to follow that perspective. I'm going to follow like that. I think the intuition we have developed is going to be good enough for what we want, so I'll define them like this. A process is going to be an Ito process if at every point in time it changes mixing two things. Mixing one, oops, this is a mistake. Sorry, this is a mistake. This is a mistake. Mistake. I've never seen this mistake before. That is that, okay? It's a mistake. All right, so again, a Ito process is a stochastic process, where my value, my variable, my process changes every point in time. At every point in time, it changes mixing two things. Mixing a certain deterministic movement, which is this one. Again, that's a typo, okay? This is deterministic. Deterministic. And this one is stochastic. And dw is the square root of dt plus minus a square root of dt. Each plus, each minus with probability 50%. That's what an Ito process is. All right. Ito studied this originally in a different context. He was trying to understand, for example, other processes such as what happens if you put something on the water, right? Imagine you have a river that's flowing and you put something in the river, then that is going to have two movement. One is somehow deterministic, being carried by the river, and the other one is stochastic, as the water has random interactions and sends the boat in random directions. I could make a joke and say the same thing will happen to a balloon that everybody's talking about. Same thing, okay? It's an Ito process also, okay? But I'm not going to talk about balloons today. I'm going to talk about stocks. Yes? But you understand, it's a mix of two movement, one random and one deterministic. But it's very important, you can mix them. They go very well together as long as the random has a size, its movement is the square root of the deterministic. So the random has to move a lot more than deterministic, otherwise there's nothing stochastic in our model, it's just a deterministic model. Okay. It's very important in doing this. Again, this is a typo. Now I see it, I cannot stand it. This DT. Okay. So it's very important that the size of this, the square root of dt, the size of that is the square root. Is the square root of dt. Okay. The deterministic one, the trend, is very persistent. That's why it always wins. That's why it has to be smaller. Otherwise, it will dominate everything, right? By the way, this means there's some moral, there's some application into, if you're a very persistent person, you will go much further than if you're a very random person. A random person will have to spend the square root of the energy of a determined person. Well, there's lots of applications in what we're doing today, right? This is application to, I guess, psychology also. Anyway, enough of the analogies. That is going to be our Ito process. We allow the volatility and the drift. So this is correct. This is wrong. Okay. We allow the volatility and the drift to be dependent on time and even of the value of the process itself. We do that. In this course, I'm not going to consider very sophisticated Ito processes. They're going to all be very simple. Well, we'll try to do sophisticated finance, not sophisticated math. We'll leave that for later. Later meaning the rest of your life. And there's a very important application of what we just learned, which is perhaps the last mountain I want to climb with you. It's an application of what we saw earlier. And it's as follows. It has some very far-reaching consequences. And it has a name. It's called Ito's lemma. Okay, Ito's lemma. Ito was the first, as I told you, a Japanese mathematician who studied these kinds of processes in different contexts, mixing stochastic with deterministic. And when you do this, there's a very interesting result, a very interesting lemma. It's going to be it's the chain rule. The chain rule that you learned in calculus, it has applications into stochastic calculus, and I'm about to tell you what it is. For that, this is what we're going to do. We're going to assume that I have a certain Ito process that has its mu and its sigma. It's stochastic and it's deterministic movement. Okay? All right. So what Ito lemma does is this. If I take my process and I map it with a function with derivatives, smooth, nice function, nothing, not the absolute value, something nice and smooth. If I map this process with this smooth function, what I end up with is another Ito process with the following mean, the following trend, the following deterministic part, and the following stochastic part. Watch. There is a stochastic part, which is this, Of course, dx contains two things. Contains one which is stochastic, one which is deterministic. But it's easy for me to guess this because if I apply the chain rule, this will be df by dx plus something here, and then df by dt. That's what I have here, right? So you would recognize from your training in calculus that because of the chain rule, this is that plus that. This is the chain rule. Everybody sees that? That's the chain rule, right? Because x is that, x is that. So if you want to know f of that, which is so it's x plus mu t dt. This dt, this is again the mistake here. Then sigma dw, right? Then what you do is partial derivative of f with respect to times that, and then the other partial derivative right here. Okay? This is the chain rule. This is the chain rule. The derivative with respect to the first variable times the change of the first variable times the partial derivative with respect to the second variable times the second variable increment. That's the chain rule. But Ito's formula does not end there. It has this term here. This term is new. It's not arising from calculus. What is this term? Let me tell you. This term is purely stochastic in nature. It has no analog in the traditional calculus. And it comes from this. When you do this expansion, there would be a term which is the second derivative of f with respect to x squared, second derivative, times x minus, I'm going to say dx squared. Okay, so times d times dx squared. In traditional calculus, this is negligible because this has one order of magnitude less compared to dt. This is dt squared, therefore we ignore it. But in our case, what is dx squared? Dx squared contains three terms. Contains the mu squared dt squared. This is bothering me so much. My goodness, that's that one, which is negligible. Then it contains mu sigma d, I'm going to say dt to the power 3 halves. And then it contains sigma squared to the power dt. Because dw squared is dt. You see? So when I look at this, it contains one part, which is negligible. Another part which is negligible, but this part is not negligible. This part we have to keep. We multiply by 1/2. That's what Taylor expansion says, and that's what this term is. See, this is a term that we pick up because of the volatility, because of the stochastic nature of this. Okay, here goes my last analogy of the day. Well, I don't know if it's my last analogy, but I think it's my last analogy. I think I ran out of analogies. There's a very interesting application of this term that we have here, which I'll say like this. If this term wasn't there, then there will be no smoking laws. You go to a lecture and you just put the smokers in a room, in a corner, and the smoke will stay there. Turbulence has a drift term in it. Turbulence is what makes fluids move faster than they would otherwise. There's an internal movement which is captured by turbulence, and that's the one here. That's another application. It's very important. Airplanes fly because of this. Oh, there goes another analogy. Do you get this? We climbed the mountain of random walks together. We saw that in doing that, the displacement has to be a lot bigger than the time increment, the square root, no less. And then we see that one application of that is that when you take an ito process and you map it somewhere, that mapping function is going to pick up an extra kick, an extra drift term arising exclusively from the volatility of the ito process. That's what we have here in the Ito's lemma. Ito's lemma is going to be key to the development of the Black-Scholes theory that I'll do next week. Okay? But I want to make sure that everybody understands what we're doing today, because it's all, I mean, the math we're doing today somehow defies intuition. I still try to do something which is somewhat intuitive, like that. I mean, I'm giving you a lot of intuitive treatment of what we're doing. I'm not doing this in a formal way. If anybody wants to do a PhD thesis on this, you will have to learn the formalism. For most of your the application of this in your career, I don't think you need the formalism, so we're going to keep it like this. Okay? Are we still together in this? Are we good? Okay, so if we are together with this, let's ignore what's in front of you now. Let's try to use everything we've learned to come up with a valid model for a stock price evolution. We are replacing trees with random walks. So what would be the right type of random walk for a stock price? That's another thing. We already know the ratio or the proportions between the time increment and the price increment. We know that. But what about the price itself? What type of ito process is it supposed to move? Let's say that I would write this down. Let me make a mistake. I like to make mistakes with my hand, or not typed. Okay. All the mistakes that I typed were unintentional. And this mistake I'm making now is an intentional mistake. What happens if I write this? Sorry. What if I do this? What if I propose that to be my stock model? Not good. What's wrong with that model? It's an ito process. Exactly. So Kelvin says this allows for negative prices, because the result of this, we know it's a Gaussian distribution. A Gaussian distribution allows any price, positive or negative. So this allows for negative prices, and stocks can have no negative prices. Why can't stocks have negative prices? Anybody knows? It's a very interesting reason. Because the stock pays you to buy it. The main reason is that stocks are limited liability companies. Do you know when the modern definition of a company was created? A bit of history now. Today I do a lot of analogies, and now I'm doing history. Do you know when stocks were created? Before the Industrial Revolution, if you had a company, companies were mostly individually owned or family owned, and then you were responsible for all the liabilities. If your company loses money, you have to pay. Okay. If you're a baker, you make bread, and then you have an oven, and you buy wheat, and then for whatever reason you don't have money and you don't pay the wheat deliverer, then they will take your house, they will take your oven, whatever you have to pay. Okay. During the Industrial Revolution, this changed because people started to, especially in Britain, in the UK in particular, they started to get together in groups to create factories and to create companies that required capital for many of them. And in doing that, they say, well, if we get together, if something happens, who's responsible? I say, well, no, No one wants to be responsible, right? So the concept of a limited liability company was created around the Industrial Revolution in England, in Great Britain, okay, wherever that was at the time. Okay, understand? And there was a necessity for pulling capital together. It would have been very difficult to do that. That means that companies, since then, they've been created with an option. The option is that you don't have to pay. There are options. This is going to be very important in a few weeks when we see the Merton model. Stocks are actually options. Kind of weird, no? Because then we're looking at options in options. There will be second derivatives. Never mind. We'll see this in detail later. What's relevant for today is that stock prices cannot become negative. The law of companies is that companies, they can go bankrupt. Going bankrupt is a possibility for companies. Therefore, prices do not become negative because of that. Okay. By the way, do you know one of the first companies ever created under this new model? Do you know? The Bay. You know the company The Bay? The Bay, the Hudson Bay. Have you been there? Have you been in their building on Queen Street? If you go to their building in Queen Street, I think it's on the south side on Richmond, check. It tells you what year it was established. Established in 17 or 16 something, very early on. It was one of the first companies. You know what the original name of the company was? You know what the company was? It was not a department store. You know what it was? It was a hunting company. Hudson's Bay Company. Yes, it was a hunting company. They were going to hunt for fur in the Hudson Bay. Okay, so the actual name was very long. It was something in the Hudson Bay. And now we only the Hudson Bay. But it was a long name, and it was a group of people got together to exploit the fur business in the Hudson Bay in the year or something. So you can check it out in the Wikipedia. I'm sure it's there. Okay. Anyway, another off track comment today. So coming back to this is not a good model for the stock price, because it allows stock prices to become negative, and a crown corp for fur, so could be. Okay, so this is not good. It allows stock prices to become negative. Stock prices cannot become negative. So what I'm going to propose to you is a different Ito process, which is this one. It's this one. Yeah? And I claim this does not become negative in price. Why? Well, let me say something, and again, I want to write this with my pen because I want to make another mistake. Watch. Who can tell me what the mistake is? I can say this is the log S equals mu dt plus sigma dw. Then obviously S never becomes negative, because you solve this equation, whatever it is, and S will be the exponential of it, right? And therefore S does not become negative. So yes, check. This could be a good model. And it is a good model. This does not allow the price to become negative, but it is not because of that. This expression I wrote here, has a mistake. Has a mistake in it. Who can tell me what the mistake is? Anybody? No? Okay, then I have an assignment for you to do right now. I'm going to give you 5 minutes. 5 minutes. What is S? S is a variable. S is a variable. This is it's a stochastic process defined like this. Okay? It's a stochastic process defined like this. So I'm going to ask you to do, all of you to do one assignment, which is to correct what I wrote here. And I'm telling you, what the mistake is. The mistake is here. That is not me. That's something else. Who can tell me what that something else is? Before you get started, okay, let me give you a hint how to do that. I'm saying here that D, I'm assuming that D log S is, what is, let's say that I call this f of S. F is the logarithm, right? What I said is that D of this is f prime of S. That's what I'm saying, right? That's the mistake I made. What is it equal to? Times ds. Sorry, times ds. Well, no, you're wrong. Who is this? Chris? No. F prime S, that is 1 over S, right? Because F is the logarithm. So, Chris, you're making the same mistake I made. Everybody sees what... By the way, thank you, Chris, for saying that. Everybody sees Chris's answer. Look at Chris' answer in the chat, please. He says it's 1s ds. And Chris's answer in the chat is exactly the same thing I wrote. So, Chris, you're as wrong as I am. But thank you for that. You gave me a chance to explain, say it in a different way. There's a mistake there. The Ito term is missing, exactly. Yugia, you said it right. The Ito term is missing. See, if we look at Ito's formula, that term should be there. That term is not there, right? I use the chain rule as you have done the chain rule in calculus. I made another mistake. So that's not right. How many mistakes today? Why? A lot of mistakes. Some intentional, some not intentional. Okay, a lot of mistakes. So I'm going to ask all of you to write the right expression for D log S equals something dt plus sigma dw. The sigma dw tells you the right one, but what is there? Who can tell me? The first one to write it in the chat gets a prize. I don't know, something. An epsilon increase on your participation mark or something. You have to use Ito's formula. Mu is mu plus 1/2. Okay, there we go. Oh, mu. Oh, okay, that's interesting. Now we have a debate. Kelvin and Theo, you have exactly opposite answers. Okay, so actually we can narrow it down to Kelvin and Theo. One of them is right, one of them is wrong. I was tempted to say there's a 50% chance that one is right and one is wrong, but no, that's not true. It's minus, so Kelvin says it's minus. So you think Theo is right? Okay. How about anybody else? Can anybody else write the answer to this? If your only question is the sign, it's kind of easy because if the function is convex, it will be plus. If it's concave, it will be minus. What's the logarithm, convex or concave? Concave, so it should be minus. No? Okay. I don't know. I still would like I would like everybody to try. You just have to do a second derivative of the logarithm. Plug it in and see what you get. I have no interest in rushing. Okay, I'd rather have everybody understand what we're doing today, because today not only we claimed a new mountain, we almost discovered a new religion, right? the stochastic world, things are not what they look. They actually have these unusual, unexpected things which are counterintuitive. Some of you may have never seen them before. Okay, I'll give you a few more minutes. I really want everybody to say Masteria. Okay, I wish I would. Yeah, please, everybody do this. Okay, believe me, it's good for you to do this. It will also help me be convinced that what you're doing is the right thing. Maybe someone else wants to give the answer. If you can do this, then I know you have understood everything we have done today. If you cannot do this, then you have not understood everything we have done today. That's why I want this to be my exercising calibration of what you learned today. That's why I'm very interested that everybody can do this. Okay, let me ask one question. If anybody has difficulty doing this, has anybody wants to confess they have difficulty doing this? It's no problem. It's no shame. Maybe either you know what to do or you have no idea what you're doing. There's nothing in between. Is someone having difficulty doing this calculation? Please say that, and then I will talk to you and make sure that you understand, and then you'll be doing a favor to other people who are too shy to confess that they don't get it. Okay, there we go. Okay, what is x and t discount? Okay, so x and t are two variables. When we did a Nito process, we chose two variables, t and x. T is time and x is value. For us, x is going to be dollars and t will be time. Okay. Ito writes these Ito processes using x because this is very general, right? It applies even to balloons, right? So not only to stocks. That's why the letter x is very convenient. T is almost always time. That's why they're processes. When you have processes, the time variable is usually time. Chris, clear? Could you go over the differentiation? Yes, of course I can. Susan, differentiation of which one? The logarithm? Yes, okay, so if I apply, let's see if I go, I'm going to remove my notes here. If I remove my notes, according to this, so f is log. You're with me there? Susan, can I call you? Susan, can I talk to you? Yeah. So Susan, so f will be log, yes? Yes, exactly, good. So that means we have that, but that we already have. This is what right? And this is this would be here, that would be the derivative of f of log with respect to this is 1 over s, right? It's good. And then you have dx, dx is ds, ds over s is equal to, sorry, I have to do a bracket here, is equal to mu dt plus sigma dw, right? Which means that ds is s times all of that, so that s kills that s, and we're done. Okay, so that part, that's the easy part. I hope that was clear. This part is what? Is the second derivative of the logarithm. Oh, there's something missing here. Oh my goodness. That was missing there. Another mistake. Wow. I guess I not only had intentional mistakes, I had way too many. I think the unintentional mistakes are more than the intentional mistakes today. Okay, so anyway, that's the second derivative. The second derivative of the logarithm would be d by ds of 1 over s, and that is minus 1 over s squared. Right? So that goes here, that goes here, and it's minus 1 over s squared. So that's why when you go here, d log s will be mu minus sigma squared over 2 dt plus sigma dw. So it's a consequence, you're welcome. So it's a consequence of the fact that we're dealing with stochastic objects. That changes into that. In other words, it's not true that this is the same as d log s. That's the important thing. It's not the same, not the same. They have different drift. Okay, so let's see, I think, so Susan, I think people are grateful that you asked your question. I think other people had the same issues. My mistake, my typo didn't help, the fact that I missed that second derivative there. But now I have a feeling that a lot of people understand this. Maybe not everybody. Could you explain how to transfer dw to... Oh, yeah. So, yes, good question. And this is how. Yeah, very good question. And so I said it, but maybe too fast. So I think this is what you mean, right? Where is this coming from? And again, here I'm missing df by dx squared. Sorry, squared. Okay? I think I'm missing that. I think I should go and fix it. I think I can. So hold on, let me fix this mistake. Okay, I feel better now. The mistake is fixed. I think I fixed it correctly. Okay? All right. So where is this coming from? It's coming from the following place. This is the first order Taylor expansion. Okay? Just so so I'm talking to okay, so Daniel is pointing another mistake. Oh yeah, this mistake. That's more difficult to fix because this is a picture. I cannot fix this on the fly. Okay, that's the key. I can remove it maybe. Maybe I can remove it. So that's a mistake. But now this is correct. Right. So let's see. I'm talking to you how now. So you agree with me? This is the first Taylor expansion of that. Yeah. That's the first Taylor expansion. You how? Are you with me? Yes. Good. Okay. Perfect. How about the second? You may think, oh, the second never is never relevant for derivatives. But bear with me, because this is not Kansas anymore. Another analogy now. Okay? We're not in Kansas anymore. We're in the land of Oz. So things are different. things are different. Okay, we have hurricanes, so who knows? So let's see what happens when I do the second order Taylor. Okay, when I do the second order Taylor, what happens? What I get is, I get, like I have here, this times dx squared, right? Plus some other stuff. I'm going to ignore the other stuff. I don't need it, okay? You can check later that it really is insignificant. But this is what? Dx squared contains this term, which is sigma squared dw squared. That term is there. You see that? You how? Yes, good. But what is this? dw squared. It's dt, right? I'm watching the chat. Until you say yes, or either you talk to me, I'm not moving. dw squared is dt. That's what I've been doing for over an hour. You're thinking, good. Thinking is wonderful. It's a great exercise. People don't do enough of it. It's better than running or playing tennis. You see, great. Actually, seeing is just as good as thinking. It's wonderful. So that means, from the last slide, yes, exactly. That means that the second order Taylor expansion has one term that matters, is this one. Of course, you multiply by a half, because second order Taylor expansions, they have a half, and that's where this comes from. So I think you, Hao, and Susan, some people are grateful to you today. It's very hard for me to predict what you didn't understand, because if I knew, I would have fixed it, right? So it's very important that you tell me what you don't understand, because as you can see, nothing here is very complicated to explain. I'm using such a simple framework. It's such a simple framework that, yeah, great. Okay, very good question. What happened to ds squared at the bottom? The thing is that the ds, good question also. This is Chris. Good question. When you do that, so when you say ds d log s, right? What you have is, I think I'm going to go, okay, well, let me say, ds is s mu dt plus sw dw, right? So that's the volatility, right? And this is this thing squared, so 1/2 the s squared that you have in the logarithm is still with that. See that, Chris? Good. Yeah, maybe someone else said, hey, what is that? What is that? Where did that come from? Yes, that's where it comes from. The second derivative of the logarithm is that. And you have to multiply with the volatility square, which is that. Okay, so maybe I do color coding of this. That is that. And second volatility, see? And that comes from that. Okay? Good. So Chris, I think you're with us. Good. Maybe everybody else. You see, there's no difficult question here. You ask, and then I can easily answer because the framework is very simple, and then you will all understand. It's very important that nothing goes not understood. That's why I wanted everybody to try this on your own. It's kind of easy to see that your sigma squared, the sign is what may be tricky, but well, you do this and now it's clear. More questions? It's all clear. Great. So that means that we have that means that we now have 3 equivalent stock models, and they're all the same. Okay, it's this. Now I can write things because now you're experts in this. This is one. This is another one. All of these are equivalent to each other. They're all Ito processes. One is an Ito process. 2 of them are Ito processes for S. They are exactly the same. This one is the same. The other one is an Ito process for a function of S, which is the logarithm of S. By the way, the fact that we are defining an Ito process for the logarithm of S, that is the reason why a lot of the, especially when we look at investments, a lot of the expressions about stock changes are expressed in percentages. Okay, logarithm is the way to consider percentage changes. That's what logarithms do, and that's why the logarithm is an Ito process which is independent of S if mu and sigma are constant. Whereas the other one, we have a very interesting effect here, which is that the drift and the standard deviation of the stock price itself is proportional to the stock price. This is important. This is what makes the stock price not negative. As the stock gets to be smaller, the volatility and the drift gets smaller too. And that has a controlling effect, preventing S from becoming negative. Okay? And this is the reason why when we talk about changes in stock prices, we usually talk about percentages, because they have the same meaning whether the stock is cheap or not. Okay, so this has implications. The fact that we came up with this formalism, it has implications. It will be especially important when we do the investment theory part of this course. And these things have named. This is called geometric Brownian motion. Geometric Brownian motion. Oops, sorry. I cannot spell. Oh my goodness, it's gone. So this is called geometric Brownian motion because it's geometric, right? That's the geometric part. And the Brownian motion is that part. And a lot of the continuous time finance theory, they are based on this. The simple models are exactly this, but even the complicated models are based on things like this. For example, there are models that what they do, and I'm not now, if you don't understand this is okay, I'm not trying to confuse you, just to tell you how far this model can go. There are models where, for example, sigma is considered to be now a stochastic variable all in itself. Okay, it's not constant, it's stochastic, so it has its own dw term, but it's a different dw, it's not the same. So then there will be, let's say that, a different one, which could be correlated to the other one, and then you have a two-factor model, and then you can do wonderful things. This is very important. This is called the Heston model, by the way, Heston. This is important because, as you know, volatility is really not fixed. You probably know of this. Do you know the VIX index? You know the VIX index? Have you heard of the VIX index? Have you heard Yeah, exactly. So Zach has. Have you heard commentaries that the volatility in the market was very high today, or very high this month, was very high this year? Volatility changes up and down, and it's not a deterministic movement. Oftentimes it's stochastic. That's why some nowadays models, which are variants of this, where the volatility is stochastic also in itself. Okay, and you can make fantastic, very complicated, mathematically sophisticated stochastic models. The purpose of today is not to do that, is to just open that door. We want to open that door. We're just going to go inside. I'm going to do the Black-Scholes theory and little else so that we have a very good understanding of this, and then we're leaving on to do something else. I'll talk about the history of risk management and climate risk. So we're leaving this. We're not doing much, but if this used to be a very big deal 20 years ago. If you like this, then my advice is write a PhD thesis on this, and then you can spend years and years writing equations and expressions, and it's wonderful. Okay? It's very interesting mathematics. If you want to be very practical, these things don't get you as many jobs as they did in the past, but it's good to know. Okay, these are things which are still extremely relevant. You have to know. No one will hire you because you know how to count. But if you don't know how to count, people are not going to hire you. Okay? It's the same thing with this. That's why everybody needs to know this theory, and that's why I will be doing the Black-Scholes theory next week. Okay? All right. So we claimed another new mountain today from the ground up. Every mountain we climbed in the previous weeks, we always started in the previous mountain. Today, we went back to sea level, and we started to climb a mountain with a lot of math, and now we've defined our stock process. The next step is going to be, not today, next week will be to use everything we've developed here. I climb to the next mountain, which is the pricing theory mountain. It's the Black-Scholes theory in continuous time. And that would be a major accomplishment, because we're bringing the two mountains together. We're bringing the previous mountain range that we climbed of pricing and the mountain we created today of stochastic. We bring them together. We climb to a mountain on top of both. That's next week. Okay? And the week after, I will be turned. And then it'll be a bit of history and some of the issues about sustainability, and which is the area where the new jobs are being created. A lot of new jobs there. So I want you to know, in case you like them, you like that theory, then you can get a job, not very hard. Okay, but anyway, I think I'm fine. I can stop class now. I think I'm happy with what I accomplished. If you have questions or not, it's very important that you reflect on this. Okay, so Kelvin loves the VIX. Great. Yeah. Don't go short the VIX though. Yeah, the VIX has a very interesting history. I just saw today. I was traveling today, so I didn't. Normally I would have done a retweet of the articles on the VIX. I didn't have time. VIX puts in 2020 per year tuition. Good for you. Good for you. Yeah, puts. Yes, don't go short. Okay. Any more questions? If not, class is dismissed, and until next week.